Hello everyone, we are from Team 2 of 2025 International Track Class. My name is Renata and my teammates are Fadel and also Sabrina. And today we are going to be presenting about our project. So our project is on the topic of NPCA-BFS Community Detection Algorithm applied to the less miserable social network. And so let's dive straight into the code. So first, let's look at the main function, which is the run npc abfs function. So this function controls the whole process. It starts by giving every node its own label and preparing the three important variables, which are labels, unvisited, and leftover. Next, the program calculates the C weight value for every node. And here we calculate the average C weight. And nodes with a value above the average become a seed node, and these seed nodes will be used to start the BFS process. If we look at this condition, if CW underscore all condition, only strong nodes can start a community. This helps reduce weak or random communities. And now let's move to the BFS part. The queue is the core of the breadth first search, and the algorithm starts from a seed node and explores its neighbor one by one. But the most important condition is the if compute row condition. This line decides whether a neighbor should join the same community or not. And if the row value is high enough, the neighbor receives the same label. So the community grows step by step through the graph. In our implementation, we use a row threshold of 3.0. This value helps decide whether two nodes are strongly related or not. Now I will hand over to presenter 2 Fadel, who will explain how the graph data and supporting calculations work.
Thank you. So before the algorithm start, we first load the graph using the build graph function. Our dataset is the less miserable network, where node represent character and edge represent relationship between them. Since this is a weighted graph, the program also makes sure every edge has a weight value. Next, we use several helper functions that support the main algorithm. The first one is edge-wake function. This function returns the wake between two connected nodes. We also use compute clustering wake function. This function calculates the C wake of node. As Renata explained, this value helps us choose the seed nodes for the BFS process. Finally, one of the most important functions is compute row function. This function measures how closely two nodes are connected by using their neighbors and edge weight. A higher row value means the nodes have stronger relationship and are more likely to belong to the same community. So, this helper function provides the information needed for the BFS process and help the algorithm make better community detection decisions. Now, I will pass the presentation to Sabrina.
So the first one, we gonna explain about leftover node processing. First, leftover node processing, after the PFS expansion, any unassigned nodes are gathered into a leftover set. To fix this, our process leftover function calculate the influence of neighboring community based on age weight. The node is then instantly assigned to the highest influence community. So slide 2 is singleton handling and final output. For communities with only one isolated node, the system loops through its neighbor, finds the strongest total connection, and merges the node into that community. Finally, land result prints the total community count which is sent directly to the visualization dashboard. And last, for the conclusion, to work out, our system relies on five key pillars: PFS proximity, data-driven weightage, smart CV seed selection, a strict row 0.30 expansion threshold, and an influence-based leftover strategy. Okay, so for the next one, we also gonna demonstrate this in VS Code. In last line, for pfs.py file, we can input the row, and here we input 0.30. It, and if we run this code, it's gonna show the information of the graph, row, community, and total nodes. See, we can see here. Okay. If we run this file, we immediately gonna go to localhost 5050. So in here, we gonna run this. Here we have two different graph with two different thresholds, 0.30 and 0.70. And we do this to comparing so we can see how the community from the and how many overlapping, so we can easily see it from the realization. Okay, so as we can see here in 0.30 threshold, they detect two community, 77 nodes, and 254 each, with zero overlapping. And the other hand, in 0.70 threshold, we have 10 community with 77 nodes, 254 each, with 5 overlapping. So here we can see that 0.30 threshold have no overlap compared to 0.70.